Let's look at this process outlined here. We've got solid water going to liquid water, that's also known as melting. If I take some solid water, is that solid water going to melt or not? And how do we know whether it's going to melt? Will it melt on its own? Whether the water is going to melt on its own is a question of spontaneity, or whether the process is spontaneous or not. If a process is spontaneous, it happens on its own. If it's non-spontaneous, then it won't happen on its own, and some energy is going to need to be put into the system in order to get the process to happen. What's interesting about this process is we know that it's reversible. It may be spontaneous for melting under certain conditions, such as the conditions when it's warm, or it may be spontaneous in the opposite direction, that would be freezing, under conditions when it's cold. And that's what we're going to start studying in this chapter, free energy and spontaneity. We want to be able to predict whether certain processes are going to happen or not. This is a discussion of thermodynamics, which you might remember when we are discussing thermodynamics. It is important to distinguish the system under study from its surroundings, and I want to just remind you of this important fact. In chemistry, when we're studying a system, the system happens to be what is outlined in the chemical equation. So the water in this case would be the system. It could be a block of ice. It might be some water in an ice cube tray. That would be the system. All of that water would be the system. The surroundings, let's say it's some water in an ice cube tray. Well, let's see. We got some water in an ice cube tray. The water itself is going to be the system. The ice cube tray, that's going to be part of the surroundings. The air, we'll say it's in a freezer. The air in the freezer, that's going to be part of the surroundings. Maybe there's a bag of peas that is jutted up against my ice cube tray. That would be part of the surroundings. The sun would be part of the surroundings. If it's in my home, I'd be part of the surroundings. And what we recognize is that, the universe, everything, is the system plus the surroundings. We generally only consider things in the surroundings that matter. So if I have some water in an ice cube tray in my freezer, probably the air in the freezer is gonna matter. The peas that are butted up against the ice cube tray is gonna matter. But the energy from sunlight coming from the sun, I'm not gonna have to worry about that because that's not interacting very much with my system. And so keep that in mind. But again, in chemistry, the system should be looked at as the entire body of reactants and products in the chemical equation under study. So what we want to know is whether this process is going to be spontaneous in the forward direction or the reverse direction. Is it going to happen on its own? Again, if it happens on its own, it's called spontaneous. And if it does not happen on its own, it is known as non-spontaneous. A non-spontaneous process is going to need to have energy input into the system in order to get it to go. Now, how do we predict this? Well, there are two things we're going to use to try to figure out whether a process is spontaneous or not. One of them is the enthalpy, which we've talked about before. The other one is the entropy. And we're going to look at the changes in these two things, the change in enthalpy, which is designated as delta H, and the change in entropy, which is designated as delta S. The changes in these two things that happen, we'll say when solid water goes to liquid water, is going to determine whether the process is going to be spontaneous or not. And these two thermodynamic functions can be linked to some intuitive ideas. So with the enthalpy tends to focus on whether energy becomes more spread out or not. And the entropy, that can be linked to whether matter becomes more dispersed or not during a process. So keeping both of these two things in mind, both the change in enthalpy during a process and the change in entropy during a process, looking at the balance between these two things, whether energy becomes more dispersed or not, or whether matter becomes more dispersed or not, it's going to actually help us determine whether a process is going to be spontaneous or not. Now, the enthalpy you've already been introduced to, and you should know for this particular process what the enthalpy change is. Is the enthalpy change positive or negative for this process in this direction, in the forward direction? Solid water going to liquid water. Well, let me think about that. Solid water, I'm just going to draw an enthalpy diagram over here on the side. And if I'm going from solid water, if I want to go to liquid water, I'm going to have to put energy as heat into that. Yeah, if I want to melt water, I got to put energy as heat into that. So for this process, delta H, that's going to be positive, isn't it? And that would mean that we have an endothermic process. So we're going to need to review enthalpy here very quickly. This is just a review. We're going to remember that for the enthalpy, delta H, if that's positive, that means energy is heat goes from the surroundings into the system. And if delta H is negative, that's the opposite. That means energy as heat goes from the system. It exits the system. So it goes from the system into the surroundings. And let's think about this just for a little bit. Which one of these two cases represents a spreading out of energy? So I'm going to imagine my ice here. Or excuse me, yeah, let's make a block of ice. Because we want an endothermic process in this case. This can be solid. So this is solid water. And that's going to go to liquid water. And this is going to go to, we'll make a little cup for it. It's going to go to liquid water. In order for this to happen, energy as heat has to go from the surroundings, so from all the surrounding stuff, into the system. So from all over the universe, energy is going to flow from the surroundings in the universe into the system. This actually represents not a dispersion of energy, but a concentration of energy into the system. So this represents concentration of energy. On the other hand, if we're going to have some liquid water, and that's going to freeze, the opposite happens. In this case, in order for this to freeze, let's just draw the equation here. H2O liquid going to H2O solid. In this case, delta H is negative. Enthalpy is going to be lost. And in this case, for this to freeze, it's got to lose energy. It's got to go to a lower energy state. Less motion of molecules in the solid than in the liquid for sure. And in this case, energy is going to flow out of the system into the surroundings. And in this case, this actually represents a dispersion of energy. So for delta H negative, this is going to represent a dispersion of energy. And I'm going to ask you, which do you think is more likely? Which is more probable? Would you think, let's just view energy as packets. So let's say I'm going to take some energy And I'm going to place it in this box here, and I'm going to stick them in a nice, neat packet, like that. And we'll have the other case where I've got my packet here, and we'll have a larger surroundings around my box. How many did I put? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so here's the two cases. Here's my two cases. We can go either direction. So I've got my system represented as this box, the little bit of, we'll call it ice. And this larger box is the surroundings. It's everything around it. And over here, this represents the same system with the same surroundings. If I take a bunch of little packets that we're going to call energy, and I'm going to throw them into this box, do you think it's more likely that they're all going to end up concentrated into the system like this? Or do you think it's more likely that they're going to be spread around the entire surroundings, as in this case? Well, of course it's going to be more likely to do this. I'm not going to throw a bunch of stuff in there and it's all going to just happen to concentrate into the system. It's going to be more likely that it'll get spread out into the surroundings. And that relates to spontaneity and enthalpy in the following way. It is more likely for processes to undergo exothermic changes, where energy is released from the system into the surroundings, than it is for endothermic processes, where energy needs to come from the system and concentrate into the surroundings. So just by looking at probability alone, we see that positive delta H, or endothermic processes, tend to be not favored, so these are disfavored, on the basis of probability alone. On the other hand, exothermic processes, in which energy gets released from the system to the surroundings, these tend to be favored on the basis of probability alone. That's kind of neat, I think. But it's not the whole story. We got to go back and remember that when we want to determine whether a process is spontaneous or not, we not only look at the enthalpy, we have to look at the entropy as well. In other words, we don't just look at whether energy becomes dispersed or not. We also need to look at whether matter becomes dispersed or not. And dispersion of matter, this deals with the entropy. Okay, so I'm going to draw it this way. We're going to stick with our H2O solid going to H2O liquid. This is going to be our system. And I'm not much of an artist, but I'm going to draw my solid water as a hexagon. I'll put some decorations on it, like this. I don't know, we'll do something like this. Make it look a little bit like a snowflake or something like that, okay? So there's my solid water, and it's got this nice arrangement. It's a very nice arrangement. And we're going to go ahead and place this in a box, like that. So that's my arrangement of my solid in my surroundings, which is designated as the rectangle. And then over here, I'm going to draw the liquid form of this. Let's see, the liquid form of this, we'll imagine this is gravity down, so the liquid form of this would probably, it's going to be spread out like this on the bottom of the container. And if we go to the gas phase, we might as well put the gas phase in here as well. That's going to represent, the water spread all throughout the system. Spread throughout the whole surroundings. Yeah? And so if we look at this process in terms of the entropy, which deals with the dispersion of matter, we're going to think of this as the dispersion of matter. It's not perfect. I'm lying to you a little bit, but it works really well to think about things this way. In which of these cases do we have the most dispersion of matter? Well, of course it's the gas. This is going to have the highest entropy, right? this is going to have actually the highest probability This is going to have the lowest probability of the three conditions. What do I mean by probability? Well, let's imagine I'm going to take a bunch of water molecules and I'm going to throw them into this rectangle, or I'll throw them into this rectangle, or I'll throw them into this rectangle. If I throw a bunch of water molecules into this rectangle, what's the probability that they're going to align in a beautiful hexagonal pattern? What's the probability that they're going to spread out willy-nilly all over the entire container? Well, this is a high probability. This is likely what we're going to see. If I throw a bunch of water molecules into a box, it's very unlikely that we're going to see this. And so what we see for a process in which we go, for example, from a solid to a liquid, let's see, delta S for that, that's going to be positive. The change in entropy, the change in probability goes up as I go from solid to a liquid. And again, comparing these two states, the liquid state and the gaseous state, if I go from liquid water to gaseous water, for that case, delta S is also positive. In the opposite direction, going from a gas to a liquid, that lowers the probability, so it's going to lower the entropy. So going in this direction, delta S is going to be negative. Let's see, going from liquid to gas, that's going to be positive. So this is another consideration that we have to take into account, both the dispersion of energy, as is envisioned through the enthalpy, and the dispersion of matter, as is envisioned through the entropy. And it turns out that processes with delta S positive are favored on the basis of probability. It's almost like a nonsense statement. You go to states of higher probability because they're more probable. It's favored because it's more probable. It's much more probable for matter to be spread out like this in a gas than it is to be concentrated at the bottom of a container like this. It's more probable for water molecules to be spread out on the bottom of a container like this than they are to be organized in a beautiful hexagonal pattern as a snowflake, such as is seen over here. So processes with delta S negative are disfavored. And we put all this together in the following way. We got to look at both delta H and delta S. We've got some possibilities here. If this is positive and this is negative, well, let's see. Let's write it over here again so we remember. Delta H, let's see, exothermic, that's negative. That means energy that's concentrated into the system gets spread out all over the surroundings. So this is favored. Delta H is positive. That's endothermic. In that case, energy that is spread out over the system, spread out in the surroundings, gets concentrated into the system. The system needs energy input in order to go. That's not likely. You're taking energy that's all spread out and concentrating it into the system. This is disfavored. All right, let's remind ourselves over here with the entropy. Delta S is positive. That's favored. You're going to a higher probability state. In other words, you're taking matter that's concentrated, say like in a solid, and you're spreading it out in a gas. Just on the basis of probability alone, it's more likely that those particles are going to be spread out. And on the other hand, if delta S is negative, then that's going to be disfavored. In that case, you're taking matter that's spread out and you're concentrating into a little area, like taking gaseous water and making a beautiful snowflake out of it on the basis of probability alone, just looking at the matter. That's probably not going to happen just on its own. But remember, we got to take these two things in concert. So we could have the case that delta H is positive, which is disfavored, and delta S is negative, which is disfavored. That's probably not going to happen at all. This is going to be non-spontaneous. So in other words, if we want something like that to happen, we're going to have to put some energy into the system to get it to go. Let's look at another case. Let's do the opposite. Let's take delta H negative, which is favored, and delta S positive, which is favored. In this case, you've got something going on where the matter's spreading out and the energy's spreading out. That's going to happen. That's going to be spontaneous. It's just going to happen on its own. Well, there's two other possibilities. We could have delta H positive and delta S positive, and delta H negative and delta S negative. Both the signs are the same. In this case, it's going to depend. It depends. What's it going to depend on? It's going to depend on temperature. And we're going to discuss that in the next lecture.